Hello.
So next up, we'll hear from Francesco on how subtyping works in Julia.
Yeah, thanks. And thanks to the fantastic author of this paper that make it possible, Julia, Artem, Ben, Jeff, and Jan. So Julia is a language that was first released in 2012, and its design is first described in Bezanson's PhD thesis in 2015. And since then, it got quite a lot of traction. So by now, there are over 6,000 packages on GitHub, and it has its own conference since 2014. At the very core of the language, there is multiple dispatch. So it is a language for mathematical computation. And let's see what we get. Let's ask, for instance, which are all the methods of the times operator. And if we do this, this is what we get. OK, now we want to understand what's going on here. So we pick up one randomly. Wow. And this is followed by some super fancy matrix multiplication code. But there are also some simpler type annotations that we can actually understand to start. And for instance, we can have a method to multiply a number by a range. We can have a method that multiplies two numbers by promoting them to the same type representation. And we have an interesting one here that says whenever you have your operands are both either signed or unsigned integers, then you can use native multiplication to perform multiplication. So how does it work in practice? What's programmer intuition? Imagine that we write times 3 and 4.0, so an integer and a float. Here there is only one method that applies, that one. So dispatch is easy. Now let's imagine that we have two signed integers, 3 and 4. Now there are two methods that applies, number, and this more specific method. I mean, if you're the programmer and you write multiply 3 by 4, you would like to have the native multiplication to be used. And this is exactly what the method that Julia will pick up. It will pick up the most specific method, which is compatible with the type of the argument. So we have to understand three things. The type of the argument is easy, because the runtime always knows the type of each value. For instance, we can ask type of 3 and 4.0, and it will say, well, it is a tuple of an int and a float. And we can ask type of square brackets 1, 2, 3, and it will say this is a monodimensional array of integers. Fine. We still have to define more specific and compatible to understand how multiple dispatch works. And this both build on the subtyping relation, and it is what I will focus on the rest of this talk. All the examples will come from compatible. The subtype relation, general intuitions, type, set of values, subtype relation, set inclusion, semantic subtyping setup, except that in some cases, Julia will depart from this interpretation, and it does this for good reasons, and this is where the fun begins. So let's see. This is Julia subtyping, actually a bit of it. And let's zoom a bit. We have code like this. So C code that uses mutable state. And it is a recursive algorithm that manages explicitly two different stacks to perform the search. OK, I can tell you that these are ingredients for a serious headache when you try to read the 2,600 lines of C code. And it is not just us. If you check the GitHub commit to the subtype.c file, then there are only 3 people that in the last year dare to modify the file, in particular Jeff. So what we have done with this work is we have taken this and we transformed it into this. What do we have here? We have a precise specification of subtyping. And since you should never, ever trust 25 different subtype rules, we built in Julia itself a reference implementation of the subtype algorithm, which is one-to-one with a different rules, with a formalization. And we have instrumented the runtime to log all the subtype queries made by running the test suite of well-known packages. And we also implemented a FADS tester. And in the end, we validate our specification on over 6 million subtype queries with a goal, which was we want 0 mismatches between the spec and what Julia really does. In doing so, we discovered subtle implementation bugs, which were all identified and fixed. Now, let's try to understand. Let's see more in detail what we got. This is not working. I start very simple, and there'll be more ambitious later. So let's see. The first thing, in doing so, I will also show all the features of the language. So if you're not familiar with Julia, take this as a gentle introduction to the language. So the first thing you can do is define types and define yourself the subtype relation. So imagine that you have a function that is waiting for a number, and you invoke it with an integer. Well, you expect this to go through. And so int should be subtype of number, so that you are compatible. And well, we can check how int was defined, and it was defined as int, as subtype of signed, and then we can check what is defined in the standard library and check the transitive closure. So what we get is pretty much this. Here there is any, the super type of all types. And if we zoom like here, we have int64. We have int64, signed, integer, real, and we get all the way to number. Great. Nothing new here. Now, some other subtyping rules comes from other constructs that we have. So we have union types, and I'm so grateful to Fabian for explaining how you subtype them. And indeed, Julia follows exactly the same rule. So if you have a union type on the left, then you have to check that float is a subtype of number, and int is a subtype of number. So that all components of your union types are subtype of the type on the right-hand side. So we have a for all quantification. Let's imagine that we have a union type on the right-hand side. In this case, it is sufficient to find one of the type in the union that is a supertype of the type on the left-hand side. And so we have an existential quantification, which lets us to the well-known rules for subtyping union types that Fabian mentioned as well. Easy until here. Julia's parametric types. For instance, let's consider this. A vector of integers and a vector of any. Are they in subtype relation or not? So if you follow the set intuition, then the answer should be yes, because on the left-hand side, we have a vector where all elements are integers. On the right-hand side, we have the set of all the vectors with arbitrary elements, and subtyping clearly holds. However, Julia cares about performance, and in its design, this chooses to represent the values on the left as array of 8-bit machine integers, and the values on the right as array of 64 pointers to boxed values. And so these are not the same. So design decision, this subtyping does not hold. We depart from the semantic subtyping idea. If you want to understand really why this is important for Julia design, check out the Julia dynamism and performance talk later this afternoon. But for now, just keep in mind, parametric types are invariant. One of the nice features of Julia is this one. Imagine that you want to have a method defined over all vectors of integers. You might write this code with a big union, which is a bit annoying. So Julia gives you this more compact way to write it. It says a vector of t where t is subtype of signed. Okay? What is this? They call it union all. It is really an existential type. To understand how subtyping works here, let's go again to a dispatch example. So let's take a simple our previous function, and let's take an argument, foo of an array of 1, 2, 3. Okay? So this is a vector of int64, and let's try to build a subtype derivation. So we have vector int64 smaller than vector t, where t is smaller than signed, and it is an existential type. Let's pick up, cleverly, int64 for t, and let's instantiate the type that we get. What do we get? We have to validate the remaining constraint. We have to prove that int is smaller than signed, which we know because it is how it was defined. And then we have to prove that we instantiate vector int 64 is smaller than vector int 64, which is also true. So subtyping union all, you have to pick a type, this second, such that subtyping holds provided once you've done the substitution. And look, there is a close relationship between exist types and union types appearing on the right. So here we have an existential appearing on the right of the subtype, a union type appearing on the right of the subtype, and they both have an exist quantification in their hypothesis. Symmetric case, if the type appear on the left, then we get a for all quantification here, like we got a for all quantification over the union types. Okay? Now, these rules are a bit abstract. What Julia really does, maybe you expect this, does a search using environment. So to rewrite this, it will actually build an environment, which is this one, introduce the variable t. And what do we have here? We have the variable t. We keep the variable name. If it has been introduced on the left or on the right of the subtype query, so that we know if it has for all or exist semantics. And we know the upper bound and the lower bound. And the search goes through by, well, here we have to prove invariance of vectors. So we have to prove int is smaller than t, given that we have no constraints on t. It is a right variable to exist. We can pick up whatever we want. We pick up int because we're clever. And we update the lower bound with int, just because we have the choice. And now we have to prove the other part of invariance. And in which environment do we have to do it? Well, in the environment where we know that t must be bigger than int. And now it is again an exist, and we can update the upper bound with int, getting t must be bounded by int in both cases. Now, these rules to update the bounds are subtle in presence of invariant constructors. You can find all the details in the paper. But in general, you can end up propagating the constraints you end up and checking if they are satisfiable. In some cases, they are not. Like in this example, so tuples are covariant. So we have vector int, comma string, and vector t where t. So by matching the first component of the tuple, we get the constraint t must be an integer, because of invariance of vector, of constructor. And on the other, the second element of the tuple will tell us t must be bigger than a string. We merge the constraint. We get that t is bounded on top by int and below by the union of int and string, which is clearly unsatisfiable. So subtyping does not hold. Fine until here. If this was too easy and you stop listening, listen now, because there will be something new. It's a diagonal rule. This is a one-line code, which is super cool. What does it do? It is defining equality for subtypes of numbers as equality of their representation. Equal, equal, equal. Now, you would say, this is not always correct. Type must be the same. And indeed, if you try to invoke this with a tuple of an int and a float, well, you should not really use equality of representation to test equality, because that would be incorrect. Okay? But it is super handy to write that code. So let's see what happens. If we write just a subtype query with the rule that I showed you, then this is a subtype query that we get. We start building the constraints. We get those constraints there, which are obviously satisfiable. And so you would say that these are compatible, and subtyping might hold. And so you might dispatch. So what Julia developers did, they added one extra constraint, which is called the diagonal rule, that says if during a derivation a variable, a type variable, is matched more than once, then, which is the case here, it is matched twice, then its lower bound must be a concrete type. It means its representation must be known and unique. And it does the trick. And it is a very simple idea, which turns out to be quite subtle to implement and to formalize correctly. This is an overview of the Julia type system. And, well, during our right across the type system, the subtype relation, we found some unexpected things. I don't have the time to go through all of them, but we show you a couple of that I found interesting. So I showed you how you solve the union all query with the environment and the propagation of the bounds, but I didn't tell you how to solve the existential query for the union types. Okay? And usually this is done by normalizing type and then applying the standard rules. But in Julia, due to a trick interaction between invariant constructor, covariant tuples, distributivity, and existential types, normalization is either, depending on how you define it, it's either unsound or gives you some rules which are not complete. And there is something super clever that Julia does. They have a super clever algorithm that explore all the derivation without normalizing, using 2 different stacks. Ask later if you want the details. Last example, to show you that the design is not only driven by theoretical considerations, but also from pragmatic implementation details. Let's take these 2 functions. Here it takes an empty union. There are no values that belong to this type, so you will never, ever dispatch to this function. Okay? And what about this one? Tuple of empty union. Again, there are no values of type empty union, so you have no values of type tuple of empty union. So these 2 functions are never invoked. They might be considered equivalent, but the types are not equivalent, because you cannot prove that tuple of empty union is a subtype of union. Because this is a tuple, this is not. Now, you might want to identify them, and so building on this, we will be able to find a counterexample to the transitivity of the subtype relation. Does this matter for programming? No, because you have to use empty union, and subtyping is used when you dispatch, and if you have an empty union, you will never dispatch, so not a big problem. And they want to keep things like this because for implementation of the runtime, they need a super fast test for the bottom type. So it must be unique. It must be an empty. Having only empty union as bottom type is what they need. So to conclude, what we tried to do with this paper, what we hope to achieve. Well, first, Julia subtyping was watched as a black box. Nobody knew how it worked. And now the programmer has precise and accessible rules of the language. For you, we tried to convince you, we hope that we succeed in convincing you that Julia comes up with an original design for subtyping that deserves to be investigated on its own. And the last thing is, well, we have a framework validation framework for Julia developers, and that allows them to explore the corner cases of the language. I don't yet know if the first 2 goals will be achieved, but for the third one, I can tell you that receiving email from Jeff saying, this is great, somehow staring at your derivations made me realize the problem, and I think I have a fix, used to make our day. Thank you.
So we have time for a couple questions because we're running a little late. Do we have any questions from the audience? Okay, well, if no one else has one, then I'm kind of curious. Is there a brief intuition you can give for this use of the 2 stacks to avoid state explosion?
Yes. One stack is used to ensure that you're exploring all the for all quantification, so they keep track of all the for all. And the second stack is used for the search of all that exists.
Okay.
And so that they can work on the type without normalizing them. If you get an error, you don't get the error on the normalized types, which gets huge, because you have seen they have big types. And the subtype queries, we got really huge subtype queries in practice.
Cool.
So, I mean, space is not exponential. Time is. But
yeah. Cool.
Thanks.
Do you have any other questions?
Do you have any idea how Julia developers use these types? How often?
So the question is,
How often do Julia developers use value types?
we have this information, and I believe that the talk of the afternoon will have precise numbers of how often all the fancy features of Julia are used. The short answer is yes, all the features are used quite commonly both in Julia people library software and in user code. Thanks.
Thank you again.